Hello and welcome to Advent of Code Day 13. Again, we are trying to solve both puzzles using Kotlin. And yeah, let's go. Day 13, Transparent Origami. You reach another volcanically active part of the cave. It would be nice if you could do some kind of thermal imaging so you could tell ahead of time which caves are too hot to safely enter. Fortunately, the submarine seems to be equipped with a thermal camera. When you activate it, you are greeted with "Congratulations on your purchase. To activate this infrared thermal imaging camera system, please enter the code found on page 1 of the manual." Reminds me of the old Monkey Island games where you had to enter a code to play the game as like a copy protection. Apparently the elves have never used this feature. To your surprise, you manage to find the manual. As you go to open it, page 1 falls out. It's a large sheet of transparent paper. The transparent paper is marked with random dots and includes instruction on how to fold it up. Your puzzle input, for example. Okay, some coordinates. Fold along. So, some interesting parsing problem maybe. The first section is a list of dots on the transparent paper. 0, 0 represents the top left coordinate. The first value x increases to the right, the second value y increases downward. So the coordinate 3, 0 is to the right of 0, 0 and the coordinate 0, 7 is below 0, 0. The coordinates in this example form the following pattern, where, what's the word for this thing? Pound? A pound is a dot on the paper and a dot is an empty unmarked position. So I guess those coordinates look like this. Then there's a list of fold instructions. Each instruction indicates a line on the transparent paper and wants you to fold the paper up, horizontal Y lines, or left for vertical X lines. This example, the first fold instruction is fold along Y equals 7, which designates the line formed by all of the positions where Y is 7, marked here with a dash. Okay, so this line is now the fold line. Because this is a horizontal line, fold the bottom half up. Some of the dots might end up overlapping after the fold is complete, but dots will never appear exactly on a fold line. Okay, so this is empty, it's our fold line, and this will always be the case, okay? That's nice. The result of doing this fold looks like this. Now only 17 dots are visible. Notice, for example, the 2 dots in the bottom left corner before the transparent paper is folded. After the fold is complete, those dots appear in the top left corner 0, 0 and 0, 1. Because the paper is transparent, the dot just below them in the result at 0, 3 remains visible as it can be seen through the transparent paper. Okay. Also notice that some dots can end up overlapping. In this case, the dots merge together and become a single dot. The second fold instruction is along x equals 5, which indicates this line. Because this is a vertical line, fold left, the instructions made a square. The transparent paper is pretty big, so for now focus on just completing the first fold. After the first fold in the example above, 17 dots are visible. Dots that end up overlapping after the fold is completed count as a single dot. Okay, how many dots are visible after completing just the first fold instruction on your transparent paper? Look at the puzzle input. Okay, those are definitely more dots. Wow, a bunch of instructions. Yeah, let's save this. And yeah, let's switch to IntelliJ and create some source folders. Day 13. And then at some point we will implement part 1 and part 2. And as always, we'll have a main function. And since that worked so well the last 2 times, I think we will again write some nice tests with the example code or the example that is given, the example paper. And then try to find our bugs in our code before we actually run the bigger code. So problem 1 again is, how do we read this? Or how we read it is quite simple, I guess. We need to figure out how to represent this. What kind of data structure do we want to use? When we had a similar problem, we actually had a list of lists so that we can have the coordinates. But since this paper is quite large, let's actually move that in. This is our input. And let's rename it to day 13. Since this is a quite large paper with a lot of dots, we might not want to do this. Instead, maybe use a list. Sorry, not a list, a map, I guess. We could map. Do we map points too, though? Doesn't matter much. We just need a way to look up points, find out whether they are marked. So we could just map it to a Boolean maybe. And we have 2 types we need to return. It's our paper with the dots and instructions. So let's say we will again have something that reads from a string and something that reads from a file, because in our tests we want to just have a string, and for the actual exercise we need a file, and the file one will use the string one. So that this will look like file name. We get an input here. And this will open the file, port read all text, and then pass it to read from string. And we still need to define what kind of things we want to return. So we have 2 types of instructions and this paper. How would we model this as a class? So let's say we have a paper data class and we need all those points, and yeah, we do not want to keep track of all points, I guess, because that maybe is unnecessary. We just need to remember the actual points. And then once we fold the paper, that is something I think what we want to do is we will have some kind of fold method maybe that will return a new paper, the folded paper, and this new paper those we can just copy over, those points that are in this case below the Y, and then the other points we need to calculate their new position, which I guess we can somehow do We essentially need to mirror those and that should be possible. And then add those to the new paper. Now we have a new paper with the new points. That is the idea. I would like to do this. So let's say we have a map. And let's also create a point, because that is on other days where I tried to use a pair that wasn't that great. And the last time I think we had a position class that had an X and a Y, and that was much easier to read. And let's say we map it to a Boolean, and it will just be true for all points that are actually in the map, and the points that are not marked, that are false, essentially, we do not even save them. Just to save space, I guess, because why would we create like this huge list that is mostly empty? I guess. I mean, we could still do this, but yeah, no. Now I want to use the map, because the folding will be easier. We just need to look at the actual points and kind of fold them. There's no need to actually look at all points, right? We only care about the marked points, so the map seems to be better. There's nothing else we need right now for the data classes, I guess, except we need to somehow represent the instructions. Maybe this will be sealed, could be a sealed interface now, which is an instruction. And then an instruction is either horizontal, I guess, fold horizontal. And that needs does it need an X? Well, that is, let me look that up. Fold each instruction indicates a line on the transparent paper and wants you to fold the paper up for horizontal lines. Okay, then we could just make it fold up, and fold left, I guess. And left will have an X value, and up will have a Y value. And then no, we will return, I guess, a pair now, which will be a paper and a list of instructions. I mean, for the first exercise or the first puzzle, we only need the first fold. I mean, we could just skip it and hard code this. But I guess in part 2 we will have to read them anyway, so let's copy this. And how do we do this? We start by parsing points, and once we hit an empty line, we switch to parsing instructions. So simple version of this is, just remember, parsing points is true, and we split the input by lines, and we need to loop over them, and this is a line now. Let's create some data structures. We need this map now. Points, it's a mutable map of point to Boolean. And then we need list of instructions, a list of instruction, and then can return a pair of this paper with points and our list of instructions. And then we need here a function call. Okay, so now we can look at the line. When line is empty, that's this line, then we switch, then we say passing points is now false. If passing points, we pass point. Let's create a helper function for this. Pass point, and we pass in the line. And if it's, oh, and we need to add this points add. And if this is not passing points, then instructions add pass instruction of this line. Pass point, and then we need a pass instruction, which we then can test it individually, I guess. Yeah, this returns a point. And this returns an instruction. That complaining here, oh, mutable map, which means we need to do put and do true. Is it complaining here? Condition is always true. Yeah, we could do else, I guess. Okay, now we only need to implement those functions. And this is the point where we could write the first test, I guess. Let's go to the test. Test passing points. Some point, we will need to define this later, and we call pass point for this here. And let's create, just copy some random ones, I guess. Say 0, 0 is one, and this one. Wanted to return those values. This, and this. And now let's do real test-driven development, and let's run it, and it should fail. While it's building, we can already start implementing this, which will be a point. And then we need the values x and y, which is line split by comma to int and y to int. Now we run our awesome test. Okay, and we do not really need to pass the instructions for the first part, but I guess we can just do it now because we will need it anyways. So we can do it quite simply, I guess, because instruction either starts with this string or with that string, and that's exactly where we might want to yeah, where we might want to check. So when line starts with this, then do something. It starts with the other one. Then do something else. And if it doesn't start with any of that, then we are in a weird case where have an unknown instruction. Just throw. Okay, let's write a quick test for that. Test parsing instructions. And let's say those. Turn them into strings. And then let's say assert equals parse instruction. And what do we expect? We expect an instruction that is fold left. Yeah, I think so. 655. This should be an instruction fold up. 447. This should be an instruction fold left for 327. And this should be an instruction for fold up 223. Close those lines correctly. Run the parser. Will fail because we only have to do's here. So if we have an X, this should be a fold up. And now we need exactly the string on the right of the equals sign. So we split by equals. We pick the second one and then turn it into an int, which in this case should just work if we would pass stuff that is not as controlled. We would need to be more careful, but here we know that we will be reading this input and we do not need to catch edge cases where, like, I don't know, the X is suddenly a long, or where it is where it's not a number, maybe a valid one. Okay, what's the problem here? Okay, one of our instructions is not actually of type instruction. That is not good. Let's run this. Okay, we mixed things up. Yeah, I was afraid of that. And that might happen quite often now. If we have, what's the fold along X? If we fold along X, then we fold left. Yeah, the test I think is right. If it's a Y, sure. The first is a Y with line on the paper. I want you to fold the paper up for horizontal Y lines. So we have a Y and this means up here. Okay, then we implemented this function wrong, I guess. If we have a Y line, we want to fold. Yeah, we mix them up. Great. If we didn't have tests, maybe that would have been awful debugging issue. Okay, but now we did it. Now we have those methods. Now we can just pass the whole thing, I guess. And test parsing from string. And then read from string. And we need our input, which is this now. And then we want to get a paper, and we want to get instructions. Read from string. Oh, did we? Yeah, we already did this here. Let's move this up. And okay, what do we assert? I guess we could start by asserting how many points we have. Assert should be 17. Does it say so? No, only 17 are visible. Wait a second, but we started with 17, didn't we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18. 18 lines. A third equals 18 paper points size. And then a third equals 2 instruction size. Awesome. And then let's just assert a random point, I guess. Paper points of point 41 would be true. Does it complain? Oh, okay, if it doesn't exist. And then let's use a random point that is not part of this thing, which is 13. Okay, let's run this. Okay, works. We've spent almost half an hour just on parsing, but I guess that is fine. So let's see, how would we implement this? Paper instructions. And this is read from string. No, read from file. And we want to read day 13 xt. And now we only want to do the first fold, and then so only care about the first one, and we do paper fold instruction, and then we need a new paper, I guess. That's our folded paper. And then we need to count our points. Folded paper count points. And then points after fold is points. So that means we need some more code. We need a function that is fold, gets an instruction, and then it returns a new paper. And then we need a count points function. That runs an int This one we can implement immediately, I guess, because it's the size. And actually, I would love to also print this, because we could print this paper. And we could print this paper just to look at it, and then that might help us debug if we want to debug this. Yeah, let's do it. I mean, that's not required, but this might be nice to actually do. So we know, I think, that 0, 0 is the top left. The thing we do not know is the bottom right, I guess. And we can just try to find it. Determine, or maybe it's the size actually, because that will be, yeah, the size of the paper. And for that we just loop over our points and need to find the largest values for x. Int, we can start with 0, so the top left. And then we could say x equals if point x is larger than x, it's point x, else is x. Why is this? Oh, we need the keys only. And then we do the same for y. And I guess we could have used the max function for that. But now we wrote it manually. And we return a point for this x and y. And then now we only need the size. Now we can start going over them. So for y in 0 to size y, and then for x in 0 to size x. Oh, do we need, oh yeah, we want to return a string because we can use this in a string build string. We can use this in a test, what I mean. And this time we trim this string because here we will need a line ending, and then here we will look up if points point xy or false. Okay, how else can we write this? What I teach you. Maybe create a helper now for this, because that is super awkward. Is marked, and we will just pass in those two. Maybe even create one for point, in case we might need this later on, because this one can just call the other one and create a point. A little bit wasteful to create all those points just for checking, but I think I can live with that. We pass in the point here. Okay, if is marked xy, then we append this, else, it's a dot here, right? Append dot. Awesome. And then we just need to return this. So now let's test. This will definitely help us verifying that the things we do here are correct, and it will help us a lot if we need to debug. Okay, this time we do not care about the instructions, and then here we paste in this, and then we pass in paper dump, and then let's take a look. Oh, awesome, that just worked. And just to make sure and to see it, let's also print it. Nice. Awesome. Now let's fold. And let's also cheat. We only need the first fold right now. So if you have an X value, we only need to fold left once. This means we only need to implement fold left. If instruction, or maybe when instruction is fold up, throw a not implemented error. Sorry, we didn't do this. Fold left. I guess we'll call this fold left. Create a function for that. And pass in the X. And if it's something else, throw unknown instruction. Okay, let's implement fold left, which needs to return a paper. So here we will create a map of new points, which needs to be a mutable map of. Then at some point we will return a paper with the new points. And here we can do the following: print paper dump after instruction line folded paper dump. And let's run part 1, and it should just be an empty paper now. Wow, this is a huge paper. Okay, let's comment that out. I guess right now it's not that important. Does it count the points? I guess 0. We could also print them before. Points before fold. Paper. Count points. Let's go. Okay. Let's now actually implement the folding. And the fun thing is we can do the test already because we know the result. So test folding left. We pass this paper. And then We have an instruction that is fold left at point Y. Oh no. Damn, the example actually folds the other way. This one folds up first. Yeah, so to pass the test, we would need to fold up first. Okay, then we will implement fold up now. I guess we will need it for part 2 anyways, otherwise that would be weird. So fold up will do something too. We'll call fold up with the Y value. Yeah. And we'll fold up. I mean, we could use the past instruction here, but I don't think that is really needed. Folded paper equals paper fold instruction. And then we assert that the folded paper now looks like this. And has 17 points. Just to make sure, this is the thing we need to enter at the end. We need to make sure the count is right. Okay, if we run this, it will obviously fail. And this is now actually testing folding up. Yeah, because it should return an empty paper right now. That's not what we want. So we need fold up right here. Test folding up. How do we do this? We essentially go through all our points and we check, is this, let's take the X, is this above our folding line? Then we can just copy it over. Maybe we start with that actually. That would be interesting. If no, we need to go over our points. Points, keys for each point. If point, the y-axis of the point is smaller than y, new points, we can just add this point here. And else if the point is larger than y, still to do. Otherwise, if it's exactly on y, then we need to no, that should not happen. Throw illegal state exception. Folding point on fold line. That should not happen, right? Because it was They can overlap here. That is not important for. And I also assume the papers will always like fold perfectly and not like in this weird shape. If I hope, I don't know. Maybe it doesn't even matter as long as we start at 0, 0 always. Let's see. Let's just try point on fold line. Yeah, let's just run this once and then we should at least have the top part. Wait, this is weird to read. Oh, this is what we expected. I'm really confused because the original one is not here. Let's remove this warning. Let's go to the test again. So this is the original one, and this is what we expect. And this is what we got. Does this make sense? Maybe. This should only be the top part, right? So 3, 1, 1, 3, 3, 1, 1, 3. Yeah, that looks good. Now let's figure out the math to find the mirrored point. What is the mirrored point? It still has the same x, but what happens to the y? This one is here. And afterwards it should be here. What does this mean? We need to calculate how many steps it's away from y, which is 1, 2, 3, and then go from y the opposite direction. So it's, y is the point. Y is this. So we take point y and remove y. That is the number of steps it's away. And then we take y minus the steps. First we calculate how fast is away, and then we go into the other direction. Okay, why is this a problem? Oh yeah, this is still point x. Mirrored point. And then new points only contains the mirrored point. Now let's run this. Okay, that was wrong apparently. Expected 2 empty lines. But yeah, there are no that's interesting. There are no points here. That's why our algorithm that finds the size doesn't see those. It doesn't know about them. It just takes this. But the thing is, for this exercise, we do not care about those. Still, doesn't matter if the paper is here or there or not. So I'm inclined to just not fix this and say, you know what? I do not care about the empty lines. As long as exercise 2 is not problem, if this is not a problem for exercise or part 2, puzzle 2, then it doesn't matter because we only care about the points. If we don't, then we need to tell the paper its size because there's no other way to figure out the size anymore at this point after folding. But as long as we do not need those, we will not implement them. So let's implement fold left because then we folding example, because now we will just run the whole thing, I guess, which means get this, and then we say paper fold, and then actually let's create another one that is taking a list. And then we say it returns a paper, right? We do not need to handle the case where the instructions are empty. This is not something we need to care about. This else case cannot happen. That is correct. So if we do not need to handle empty instruction lists, we can just say start with the current paper, return a paper at the end, and then we say instructions for each paper fold instruction, and paper equals the folded paper, and then return it. Awesome. And then we can say perform all the instructions that are coming from here. And then we just need to assert a dump. And that should look like this. And I keep the last line, but it will complain that we do not have them, and then I will remove them. So if we run this, it will fail because we didn't implement one of the functions, and that is folding up. As we can see, the up fold is definitely missing. The left fold. Okay, kind of confused. Why? Why this is still so large? Looks like it didn't do anything at all. Fold. Well, let's start with folding left, I guess, and then we will see. Yeah, that will be kind of the same, but different. We go over all points, then if point x is smaller than x, then we can just copy it over, right? Let's look at the example. So if it's already on this side, doesn't matter, we can take it. It is. So new points, point. If it's larger, then we say something fancy. Otherwise, we throw, like here, let's run it once. You know what is super weird here is at the point where we didn't do this thing, we should have ended up after the fold left with an empty paper. But we didn't, which makes me wonder what kind of instruction did we actually execute. Let's make sure we actually got the right instructions. So first we have a fold at the Y, which is a fold left. 7. No. Starting again, mixing things up. Fold up. This is instruction 0. And we have instructions 1, which is a fold left with x5. This is correct. And we start with the current paper, we fold it according to the instructions and then return the paper. Why is this not an empty thing now? Already a mistake here, because this is a new mutable map. It returns a new paper. It should have run into fold left. Let's print this here. Instruction. New paper. Pardon. Ah, now it is an empty. Do we print the wrong one? Yeah, we do. We do not even keep reference to the folded paper. No, folded paper. Now we dump and let's go. Yeah, okay, that is now what we expected. An empty, small, tiny paper with nothing on it. Sad. Okay. Now we do the same, I guess. Steps and steps. Let's look at this one. So it's the large one, the point x minus the x. This is the steps, and then the new point will be at something something same y. Point y. So this time we take this point. No. We take the y, the x, and minus the steps, which is kind of what we did here, right? Y minus the steps. Yeah, I think that looks good. Let's this. Funny. Something funny happened. We ended up without some points. Those should be missing, but those are weird. What did we do wrong? We take the x of the point, subtract x, this is the number of steps, then we take the x and minus the steps. This one will end up here. X minus the steps, yes. Why is this not the case? The paper looks like this. Now our result looks like this, which is weird. We need to look at the steps again, I think. Let's write the test. And instructions for each. Let's print it. And then we say Need to keep track of the paper. Folded paper now equals paper, and then we say folded paper equals folded paper fold this instruction. And then we print the paper. And then we just look at this thing. So this is the fold up. After the fold up, it looks like this, which is correct. But then the fold left, 0, 1, 2, 3, 4, 5. The fold left is absolutely wrong. Looks like we didn't even add anything, so maybe we did. Yeah. Yeah, okay. We didn't even add anything. And I bet people who actually looked at this video have seen it immediately, and I was totally confused. What is happening? Let's add the mirrored point. Now everything should be awesome. Yeah, now our debug looks great. So let's, where are we? We can remove this debug function, run our test function. Now it should only complain about the bottom row, which we do not care about. Yep. So remove this for now. Awesome. And I think now we should have everything to run instruction 1 for part 1. We end up with 729. Awesome, that's the right answer. Here comes part 2. Finish folding the transparent paper according to the instruction. The manual says the code is always 8 capital letters. What code do you activate the infrared thermal imaging camera system? Interesting. So maybe we actually need our dump at the end. Right, that was smart to do. Or at least not wasted time. Now we fold all instructions and then folded paper dump. We dump our folded paper. Let's execute part 2. Ooh. Oh, that is not easy to read. Is this how it should be? Or did we mess it up? That's an R. That looks... It almost looks like we have a mistake somewhere, do we? Might be a 6. Z. L. Well, those characters look right. B. And H. F. P. That is not the right answer. If you're stuck, make sure blah blah blah. This is an R. 6 Z L. Oh wait. No, this is a B H F P. Okay, now I'm confused. Like the Z and the L, they look all great, so I assume our folding is definitely done right. Is it just oh wait, this is not a 6, this is a G. Now I can see it. Okay, let's do it again. Oh, with a G. 8 capital letters, yeah, can't be a 6. Awesome, that's the right answer. We'll remove this here before uploading this to GitHub again. And yeah, if you like this video, please leave a thumbs up. And yeah, let me know in the comments how you solved the problem. And yeah, I'm really happy we wrote this dumb function because we actually needed this. I don't think it was required to implement some weird character detection algorithm. Well, you couldn't do it without dumping it first anyway. So, thank you for watching. Bye bye.